Right. Good evening, class. Okay. So I'm taking over the part 2 of this course. Right. This is my name. Okay. The overview of the part 2. Mainly we're going to introduce the control system design. We'll start with the simple one, and then we'll increase the complexity of one step at a time. So there are 6 sessions. Then I will give you the references. Of course, those are you are not required by them, right? That's if you're interested, you can borrow them from the library. But the materials, most of my materials are available. I will give you the lecture notes, tutorials, and also the PowerPoint slides. I'm also will give that to you. Okay. There is one mini project that you'll have some hands-on experience on how to design a control system. Okay, I will release this lead project very soon. That will count for 30%. Then your final exam, of course, that will be 70%. Okay, to do this lead project, you are required to use the MATLAB with Simulink toolbox. Okay, if you don't have any experience with MATLAB, of course, you have to learn that by yourself. We don't have time to cover the coding part. But for all the students, you can install MATLAB for free. Okay, you have learned many things. In part 1, of course, you may think that is very mathematical course, right? Okay, but part 2 is about the controller design. So before I move on to the theoretical details, I just show you our educational video, show you what is this course all about. Okay, how the feedback control can improve the performance.
Hey guys, welcome back to Control System Laboratories. I'm working on my big flashy entrance here, so hopefully I can grab your guys' attention right off the bat. And, well, now that I have you, in this video I want to show you guys a really simple feedback control system for a robotic car, like this one. And in doing so, I want to show you sort of the differences between commanding open loop versus commanding closed loop, and how closed loop control can help you meet your design goals for your system, even in an environment that's changing due to disturbances or just uncertainties in the environment itself. Now, before we get started, let me really quickly show you the components that make up this robotic car. So this is the robotic car that I'm going to use as my test platform. It's mostly just a stock Zumo robot from Pololu.com. I got the kit rather than the fully assembled vehicle because I wanted to practice my soldering. But if you're not into that, you can always just get the fully assembled car. Now with the kit, you get to pick your own micro metal gear motors, and I chose 2 of the 50-to-1 gear ratio high-powered motors for my project. These 2 motors are the ones that drive the front wheel for each of the left and right side. Now, the Zumo Shield, which is this big black printed circuit board, can be modified to interface with various versions of the Arduino microcontroller. I set mine up to work with the Uno, because that's the one I have, and the instructions tell you how to do this, but basically it's just soldering these header pins in the right pattern so that it matches the Arduino. Now, the Zumo Shield has a few sensors on it that you have access to. However, I wanted to use an external sensor because I think it makes more sense for this educational video if you can actually see the sensor that I'm using. And that's why I have these wires protruding from the front here. They allow me to connect to this I2C external bus component. Now, I2C stands for Integrated Circuit, and it's a way to send information between 2 different ICs, much like a telephone wire between a sensor and a microcontroller. Now, if you don't know what any of this means or how to write code to read an I2C device, Don't worry about it. There's a few libraries online for the Arduino that do all that work for you, and I'll get to that in a second. Now, as far as my Arduino, this is unmodified. It's just an Arduino Uno, and I happen to stick this breadboard on the back using the adhesive that comes with it so that I have a place to attach my external sensor. And if I put this all back together, you can see what the final product looks like. And again, I can plug in my I2C bus into the breadboard, and then I can plug my I2C component into the breadboard also, so that everything can now read each other. Although for this first example I want to control the car open loop, so I'm going to remove the sensor for now, and let's go set up the test. Now I want to have the car drive from this side of the platform over to this side and make it to this flag. Now it's just a straight line, and I've drawn the straight line in black here on the platform so you can see it a little bit easier. But the trick is I want to command this open loop, which means I need to be able to predict how to send commands to the car in order to accomplish this. Now, luckily it's just a straight line, so that makes it pretty easy. All I have to do is send the exact same command to both wheels, and if I built the car correctly, they'll both spin at the exact same rate, and the car will just drive in a straight line across the platform. So let's go write the code for that and test it out. Now, if you're not too familiar with writing embedded code, don't worry, neither am I. But luckily you can download the Zumo libraries for the Arduino directly from the Pololu website. You can either just do a search for the Zumo Robot Kit, or you can click through the links to get to it. But once you're there, click on the Resources tab to find out all of the different files that you can download. And under the Zumo Shield Libraries link, you're going to find the files that we're looking for. And there's libraries here to drive the buzzer, the motors, the sensors. You can download all of them if you want, but we're only going to be using the Zumo Motors library for this example. To download them all, just click the zip button up at the very top. And once you download them, put all of the files into the library folder for the Arduino, so that you have access to these libraries when you open up the Arduino application. Here I'm opening up the Zumo Motor example. This code will show you how to access the functions in the Zumo Motors library so you can control the car. It turns on an LED when driving the car forward and then turns it off when driving backwards, so you can see if you accidentally wired the motors wrong. I didn't, so I'm going to remove this LED code for our example to make it a little bit simpler. However, I don't want the car driving as soon as I turn it on, so I'm going to add a 5-second delay here at the beginning. Now down here the code cycles through running each wheel forward and backwards to test that they're working. Again, I don't need this code. I only started from this so I could see the syntax for commanding the wheels. Also, I'm just going to set both the right and left motor speeds to 100 counts. Since the max is 400 counts, this should drive the car in a straight line at about a quarter of its max speed. So this code will run the setup once upon initialization, which is just going to wait 5 seconds. Then it's going to run the loop function continuously until you remove power. Let's compile this onto the car and go test it out. So I'll put the car down here on the test platform, and it's got the 5-second delay, so I turn it on, and we'll watch it go. And pretty much as expected, it drives in a straight line right towards the flag. But what if I try that again, but this time add a little bit of disturbance into the system? Let's see how it works then. Alright, I'll set this car up one more time on the end here, and this time I'm going to rotate the platform while it's driving. And as you can see, it's not going to make it to the flag at all. In fact, it's just going to follow the rotating platform. But that's okay. If we know ahead of time how the platform rotates and at what speed it rotates, we can still command this open loop. We just need to make a few modifications to the code first. Now we want the car to turn to the right, so in order to do that, we'll just increase the left wheel speed a little bit and decrease the right wheel speed a little bit. So let's compile this code and put it onto the Arduino and go test it out again. Okay, now that we have our code uploaded onto our car, let's try this one more time. This time we'll add disturbances to the system. As you can see, the car is rotating off of the black line, and it's still driving right towards the flag. So as long as the disturbance is exactly what we predict, open loop commanding still works just fine. But I think you can see the problem here. If we try that one more time, and this time we don't add a disturbance, or we rotate in the wrong direction, you'll see that the car doesn't go anywhere near the flag. And this is the main drawback of open loop commanding. if you don't know your system perfectly, or it's not robust to all of these different variations in the system or to disturbances to the system, then open loop commanding isn't going to work. You're going to have to add a sensor to the system and command it closed loop. So let's go try that. Okay, the sensor that I have is called the MIN-IMU-9, and it's from Pololu, and it's called an IMU, which stands for Inertial Measurement Unit, because it houses a 3-axis accelerometer, a 3-axis magnetometer, and a 3-axis rate gyro. And it interfaces with an I2C bus just like we want. However, for this example, we're not going to use all of the sensor readings. I only want to use the gyro. We could have also chosen the magnetometer reading, or both of them in conjunction for our example, but I'm just going to stick with the gyro to make things simple. Now, I'll talk about how I set up the control system in detail in a future video, but first let me give you the big picture of what's happening so that you have an idea of how I did it. Now, the first thing is that I still want the car to drive forward at about the same rate, so I'll still command each wheel to run at 100 counts. And this is just an open loop command to both wheels since it's not based on the actual state of the vehicle. But in addition to this, I want to drive the angular velocity of the car to 0. So that's my reference command, 0 omega. Or in other words, I don't want it to rotate in inertial space. That way when I rotate the platform, the car will try to stay driving forwards towards the flag. So my reference is 0 radians per second. I'll compare that against the measured angular velocity from the sensor to generate my error term. The error term then goes through a controller, which in this case is a proportional controller or just a simple gain. And the output of the controller then is the delta wheel command. And I'm going to add that delta wheel command to the right wheel and subtract it from the left wheel to generate our turning moment on the vehicle. Now, one thing to note at this point, that as long as the sensor measures no angular velocity, then the error term is going to be 0, and each of the motors are just going to get their original 100 counts each. Now, the left and right motor commands go into our plant, which is just our Zumo robot, and then the plant generates an angular velocity for the vehicle. And of course, our rate gyro is going to sense that angular velocity of the vehicle and will feed that back into our controller. But one last thing, the sensor might be a bit noisy, so I wanted to add a simple filter to the output before it gets over to the comparator. Now I'm going to talk more about filtering in future videos as well, so don't dwell on that too much right now. So this is the simplified block diagram of the control system, so let's go over and see how we'd write the code for this. Now the first thing that the code does is declare the variables that we're going to use later on, as well as set all of the include files. Now the first bit of code inside the setup function just sets up reading the gyro, and this is just stock code that I got from the gyro example off the website. Again, also I have this delay 5000 which just waits 5 seconds before commanding. Inside the loop function we just read the gyro to get the angular rate of the vehicle, then we build a 5-frame averager filter which just averages the last 5 readings and puts it into variable g. So now our left motor speed velocity is just 100 minus g divided by 35, which is g times the gain of our controller. And for the right speed, it's 100 plus g divided by 35. This difference is going to give us the turning that we need in order to respond to the angular velocity of the vehicle. And lastly, I put a delay of 50 milliseconds here because I want this loop to run at 20 Hertz. So let's go back to the test now and see how this works out. Alright, let's try our closed loop control system in action now. I'll set it up, and just like I did before, I'm not going to add any rotation to the platform. And you'll see that the vehicle is still going to just drive straight down the black line right towards our flag, exactly like it did in the open loop case. But now we have closed loop control. Let me show you kind of what's going on here. If I don't rotate the car at all, both wheels are going to rotate at the exact same rate. But as I rotate one way versus the other, you'll see one wheel stops and the other continues. So, let's try this one more time. And this time I'm going to add some disturbance to the system and see how our closed loop controller can handle that. If I add some rotation, you can see that it's going off the black line and driving, well, more or less towards the flag. There's probably a little more tuning that I can do with the control system to make it a little bit better. If we watch that very same thing though from above, it's a bit easier to tell what's going on. So as you can see, our control system does a pretty good job of rejecting disturbances and still being able to maintain its goal, which is to get to the flag here at the end. Of course, we can always improve on this control system. We can make it faster, a little bit more accurate, work in a wider variety of environments. And we're going to do that exact thing over the next few videos. I'll keep this.
Okay, all right, just stop here. Just make two comments. First of all, right, I mean, the reason is that we need to use feedback is because, right, the uncertainty, right? We don't know how the platform rotates, if it may rotate clockwise or anti-clockwise, right? You don't know, and probably there are some other disturbance like a wind blowing on the vehicle. So unless you have the perfect knowledge about the uncertainty, you can use the open loop control. So to deal with these uncertainties, well, we have to use the closed loop control. Okay, that is one point. The other point here, the controller we use is just a proportional control. That's why you may notice that it does not follow a straight line perfectly, right? There is some difference, but that is because the simplicity of the controller. After you learn this course, you will know how can we make the output error to go to 0 instead of a finite term. So I will close this. The whole purpose to show this video is to let you know that this whole course is not about mathematics. It's about how do we use the feedback to improve the performance of the system. Okay. So we have a system we want to improve the performance. Of course, there are many examples in the real world, okay, which implemented the control system. And the output is the variable we want to control, okay? Like the temperature of this room, right? If we use air conditioning, the temperature of this room is the output we want to control. Okay, and then the desired reference, that is the desired output we want the system to achieve. Okay, and then when we say feedback, means we have to measure the output. Okay, so we have to sense what is happening in the environment, right? With that information, we say, okay, we measure the output, we compare to the desired output. Then we know whether the system is behaving correctly or not. We have our error signal, okay? And the purpose of this controller is try to minimize this error signal. Okay, that was what we call the feedback. Okay, many feedback, of course, is everywhere, right? We humans also use feedback. Right? We have to know what is happening, right, in the real world and use that information to improve the behavior. So that's a very simple idea, but with that idea, you will see that it's very powerful for us to design the controller to improve the performance of the system. Okay, the objective will try to design the controller such that there's difference, right? Difference between the output and the desired reference as close as possible. Okay, so that is the overall picture of the second part of this course. And also I already showed you the video, a simple control example, which involves both the hardware and the software parts, right? That such that you have a sense of what you are learning today, well, in this course, will be applied to many other real applications in the world. Okay, let's start from the how do we specify the desired output. So we want the output, right, the real output to follow some desired output. Then how do we specify that? Can we make the output of the real system follow arbitrary command signal? Okay, in this course, I'm going to ask you a lot of questions. Now, you don't have to raise your hand to answer my questions, so that takes too much time. Just speak up. Whenever you know the answer, you can just speak up. Speak up, and then we will move on. Okay? Can we make the output follow any signal? For example, can we set our desired temperature of this would be 100 degrees? We cannot, right? We cannot. So has to be reasonable, right? So therefore, the reference signal is usually generated by a well-behaved reference model. Of course, to do that, you have to have some sense about the property of the physical system you are dealing with. Okay. Now, first we'll try to build a reference model, which will meet all the performance requirements. Okay, so we'll build a reference model which can meet all the performance requirements, and then we'll try to build the controller which can follow the reference model. Then if the reference model can meet all the requirements, then we believe the closed loop system can also meet the requirements because it can follow the reference model. Okay, that is one way to do that. Then the next question is, of course, is how do we specify the appropriate reference model in practice? Then, of course, this will depend upon the design specifications, right? What is the requirements, performance requirements you want the system to meet? Okay, there are many ways to build the reference model, but the simplest way is to use the second order system. The reason is simple because the second order system, right, is well studied. All of its properties are perfectly known. This is just if you look at the transfer function of the second order system, of course, that is a typical oscillator, right, with some damping. This zeta is the damping ratio, and the omega is the electrical frequency. Those two parameters will completely characterize our second order system. Okay, and then this is the typical step response of our second order system, right? So the system output will first overshoot, right, and then it will settle down to some final value. Okay, and then we have some terms to call this. Okay, say how long it will settle down. Well, we call the settling time for the output to finally settle to some value. Of course, in theory, it will go to some constant when time goes to infinity. But we say actually when it settles down to some like a 2% plus and minus, right, of the final value, we call it is already settled down. Okay. So this here we say, and then the meaning of the overshoot, of course, this is obvious from the graph, right? It will overshoot the final value, and then it will oscillate, and the overshoot ratio, right, will be related to the damping ratio of the system. So we have those formulas which relate those time domain specifications, right, like the settling time, the rise time, and the damping ratio to the parameters, the damping ratio and the natural frequency of the system. So those formulas are completely known, okay, in theory. So that's why once you know, okay, what are the requirements on the settling time, the overshoot and the rise time, and then you can design the proper value of the damping ratio natural frequency, right? Therefore, you know that then in this way you can build the reference model. So you know this reference model can meet all the requirements. Okay. Here again, I just show you some of the design principles of basic idea how to design the speed control system. Okay, but first let you have a sense about what is the speed control system in the real world.
The MAN Adaptive Cruise Control Driver Assistance System for trucks and coaches automatically regulates speed and distance from other vehicles. ACC is an intelligent development of cruise control which also controls vehicles' brake systems. ACC autonomously ensures that a speed-dependent distance defined by the driver is kept from vehicles in front, which is particularly useful for long periods of motorway driving. Traffic safety is considerably enhanced by automatic adherence to the correct safety distances. The new MAN ACC system achieves this with two independent sensor systems using radar and camera. Together, they monitor the space in front of the vehicle. The radar sensor detects vehicles in front and calculates their speed, distance and position in relation to the vehicle in which it's installed. The camera on the windscreen boasts autonomous object recognition and also detects lane markings. The camera and radar communicate constantly with one another, comparing their individual results. This means that the vehicle in front can be detected with maximum precision and reliability, even if the road layout is complex. The MAN system with its camera and radar is significantly more reliable on winding country roads than systems that rely solely on radar. If ACC detects a slower vehicle in front, it autonomously adapts the speed to the driver in front and ensures that the required distance is kept. If necessary, ACC will brake using the retarder and main brake. If the driver in front accelerates, the ACC returns the vehicle to the originally selected speed. The driver chooses his preferred speed on the multifunction steering wheel. Using a rocker key on the dashboard, the driver can also set the distance from the driver in front in 4 steps. A central display provides the driver with information on his settings and any actions taken by the assistance system. If ACC detects that there is a vehicle ahead, the system displays its speed and distance. The driver is also alerted.
All right, that gives you some idea of the real applications of this speed control system. Now let's look at the basic theory behind all those control systems. So here, just one example, you have there is a vehicle, you load the mice, and then you load the friction coefficient. And then you can design control system such that the vehicle can reach 100 kilometers per hour, right, in 8 seconds with overshoot less than 5%. Those are the performance requirements you want to meet, right? Those numbers, 8 seconds, that refers to the settling time. Okay, the 5% refers to the overshoot. So you want the system to have those performance requirements. Okay, and of course, you need to build a model. Of course, this model is very simple. From the Newton's second law, right? This the change rate of the momentum, right? Equals the force, is engine force, so is the friction force, right? And then you build the model. Okay, once you have the model, but of course here the x is the displacement. If you're interested in the speed control, we say we can just use y. That is the output. So we can rewrite the equation for the output. And then we have our first order system to describe this speed control system. So this is the modeling of this vehicle. Here comes the part how we're going to design the reference model. So we build the reference model. When we build the reference model, right, the key is to try to meet the performance requirement. So we have 2 numbers. Well, one is the overshoot, the other one is the settling time. For the overshoot, normally we work out the requirement of the overshoot first because overshoot is related to only one number, the damping ratio. Okay, we have this formula, right? We have also have this graph, but okay, here you first try to solve. Let's say we know that the overshoot will decrease with the damping ratio, right? So we set this one to be 0.5, then you get this number. As long as the damping ratio is bigger than this number, then the overshoot is always will be smaller than 5%. Okay, of course, you don't want to use this number, right? You want to try to use some simpler one. Consider 0.7. Let's say once you set this as 0.7, okay, this is the damping ratio which can let you meet the requirement on the overshoot. And then from the requirement on the settling time, you can set your lateral frequency, because the settling time, right, is related to the damping ratio and lateral frequency by this formula. Okay. So, okay, here you may notice that, I mean, if you are taking the other course on computer control system, you may notice that there is a difference in the numerator. Right, in that course, we set this numerator as 4.6, but remember that one, the settling time we define as the 1%, 1% settling time. In this course, right, we set 2% settling time, so here is just 4 over zeta omega n. And from this one, you can get your lateral frequency. And of course, why we set this number such that we set those, damping ratio lateral frequency in this way such that the overall transfer function will be very simple with a very simple number, will be like this. Okay, just for the simplicity. But with this reference model, it can meet both requirements. Okay, that's the way you design the reference model. And then the next job, right, you want to build the controller such that the closed loop of the system, right, can match this reference model. So now we talk about the reference model, then we say, okay, we will try to build a controller such that, right, the closed loop transfer function can match the reference model completely. Ideal case, we may have a perfect match, right? If you know how to design the controller, and then also there are certain conditions for perfect match to happen. But in reality, right, we may just have to match one of them. First, okay, there are two parts to match. One is match the denominator. So try to make this closed loop, the transfer function of closed loop, right there. This is the denominator of this transfer function match the denominator of the reference model. This one we call the pole placement, because if we match them, the two systems will have the same poles. The roots of the denominator, right, are the poles. And then, if you want to have a perfect match, we also have to match the zeros, right? Then we call the zero placement. But which one is more important? If you can just match one of them, so which one is more important? Of course, the poles, right? Because poles decide the stability. For whatever control system you try to design, the stability, that is the first requirement, right, you want to meet. After that, then you try to meet other requirements, right? Okay, so that's the reason why today we're going to talk about how we're going to solve the pole placement problem. Okay. Then we are going to use a very simple controller. We say it's state feedback. State feedback means that we are going to use the state information. Here, of course, here this location, right? The state space model, right? You have been studying this for the past 6 weeks, right? Now you are familiar with the location. We have this x star equals ax plus bu y equals c times x. Okay, for this part, we assume that the input and the output may be multidimensional. Okay, which means, okay, there will be multiple inputs or there may be multiple outputs. This is the main difference between this course and the other course on computer control system. Okay, if some students are taking the other one, the other course we are mainly talking about the single input, single output course. But for this one, we are going to talk about how we deal with the multiple input, multiple output course. So, okay. Now, with that setup, let's ask the question, what is the simplest feedback controller? You can imagine, well, what is the simplest feedback controller you have learned in the past? Okay, PID. Of course, the simplest one of the PID is just the one used in that educational video, right? The proportional control. Just use P. So proportional control, the idea is very simple, right? Control input is just proportional to the error signal. Let's just try the simplest one first, right? Then we say, okay, here we have the state information from we measure state. We assume right now we assume we have the sensors to measure all the state variables. Okay. Then at some point we were going to introduce our way to say, okay, if what happens if we don't have only one sensor to measure the output, we can still cope with that, but we'll leave that to the later part of this module. But right now we just assume that we have the sensors to measure all the state variables. Okay, for power placement, the objective, right, is stabilization. So therefore we want to drive, let's say we want to drive the state to 0. Therefore here we say, okay, actually the desired state is 0. Okay, then the error signal, of course, just the desired state minus the real state. That is the error signal. And the proportional control is just we put again to that. That is how we get this proportional control. Of course, here is an extension of the proportional control. When you were undergraduate, normally when you're proportional, it's just proportional to the output, one signal, right? So but here, this x, right? X is not a scalar. X is an n-dimensional vector, state vector, okay? But also, the input, right, is not a scalar either. In this course, well, we will deal with the case where you have multiple inputs. So therefore, your input is n-dimensional. You have n inputs. This is m-dimensional, this is n-dimensional. Then what is the dimension of this matrix, K? So of course, would be m times n, m times n matrix to make it work. Okay. So therefore, there is a matrix again for us to design. It's not one number. It is not just a vector, like in the case for the computer control system where you have only one input. Here we need to design a matrix. Okay, of course, this is just a purely feedback term. We may also add a feed-forward signal such that the final form of the controller would look like this. This is the controller we're going to use for the rest of this module. Okay, we're not going to delve into the nonlinear control. So here is what we call the linear control. Okay, so the input, right, is just a linear function of the state variables. And we want to design K, we want to design F, right, for some of the controllers. But for pole placement, because we're only interested in the poles, or we only need to design the game matrix K. So X is the state variable, right? R is the reference input or the command signal. Okay, so we want to design K. Let's see how we're going to do that. So we just plug this controller right into the equation of this x dot equals ax plus bu, and say what happens. So we plug this equation of the equation that you are so familiar with for the past 6 weeks, where x dot equals ax plus bu. Then this one we get, so because we have to multiply by b, then we get minus b times k. Right, we merge group that together with, because they're all associated with the state vector. There is an additional term. This comes from the reference signal, but like I mentioned, right now we only focus on this one, right? This one, a minus bk, and how we're going to design k. Remember, without the feedback, right? Without the feedback, the system is described by x dot equals ax plus bu. Now with the feedback, you will notice that the matrix, right, has been changed from A to A minus B times K. That will make a huge difference. Okay, that is the magic of the feedback control. From this one, easily you can see, even if the open loop system, right, is unstable, if A is unstable, but with the help of the feedback, right, this closed loop matrix A minus BK can become stable. Okay. Of course, on the other hand, right, if you don't design your feedback gain properly, if your original A is stable, but with feedback, it may become unstable. Okay, so it's a double-edged sword. So whenever you use feedback, it means you are going to change the property of the system. Okay, therefore, you have to be careful, right, to make it work. You don't want to destabilize the whole system. The positions of the poles, of course, now you know that correspond to the eigenvalues, right, of those two matrices. You want to, the eigenvalues of this original matrix now can be changed to other eigenvalues, which will depend upon how you design your gain matrix K. Okay, any questions? So in this course, I understand, of course, the math is quite heavy, right? So I try to explain all the derivations, since now you are the graduate student, you are supposed to understand all the derivations. Okay, then in such a way that you can do it by yourself. So although I ask you a lot of questions, but whenever you cannot follow, you can always ask me questions. But in the class, then I can answer your questions. That can also help your classroom. Okay. So let's summarize what we have learned so far. So why do we want power placement? Of course, because we want to meet the time domain requirements for the control systems, right? The system I want to be stable, not just stable. I want it to meet some of the requirements, and those requirements in many cases can be specified as some time domain specifications. In many cases, right? Those are the commonly used one. We look at the rise time. The time for the system output to reach 90% of its final value from its 10%. And the settling time, that's the time for the system transit to and stay in a final value around its final value, say 2%. The overshoot, that's the maximum amount by which the output overshoot is steady state value, right, divided by its final value. So it's often expressed as a percentage. Graphically, right, it's much easier for you to understand those three numbers. Those are very commonly used one. Okay, and we know that for the standard second order system, right, we have the perfect knowledge about that. Then we know how those time domain properties are related by those two numbers for the second order system, the damping ratio and natural frequency. Those formulas, right, are well known. They are given in the textbook, right? Also, you can derive it by yourself. Okay, But then there is another question is that, okay, you may ask, that is only for the second order system, right? Second order system, but in reality, the order of the system may be higher than the second order. So how are we going to deal with the higher order system? Well, how are we going to specify the pose for higher order system? Here, the key, right, or the simple idea is we can use the dominant mode to approximate any system, right, with an order bigger than 2. Okay, here I just give you one example for you to understand the idea of how we do the approximation. If you look at this system, clearly it's a combination of our second order system and then there's a first order system, so there is a third order system, right? There are 3 poles. Okay, and then you try to analyze the poles, so you compute the poles easily. You get those a pair of complex poles, and there's another one, right? Is a real pose, and then you try to identify the slow mode and the fast mode of the system. So how are we going to do that? We know if there is a pole, let's say at -2, right? We know that its response will contain this term 1 over s plus 2 by partial fraction, right? You know, okay, this 1 over s plus 2 will, because it's a part of the transfer function, that will, which means in the time domain expression, right? There is a component e to the -2t. Then for this pole, this pair of the complex pole, right? So actually, it means there is a time domain expression expressed by this one. Okay, there is a, this is the amplitude, and then this is the oscillation. We know the amplitude will decrease to 0. Okay, if you look at those 2 modes, right? One is described by e to the -2t. The other one, the amplitude is e to the -0.5t. So which one will decrease faster to 0? E to the -2t, right? Of course. Now, so the bigger value of the absolute value of the real part, the faster it goes to 0. To approximate the system, we want to throw away some of the modes, right, and keep the other mode. Okay, shall we throw away the fast mode or throw away the slow mode? Which part should we keep? We should keep the slow mode, right? Because the fast mode goes to 0 so quickly. Does that make sense? Right? The dynamics of system will be dominated by the slow mode, and the fast mode can be ignored because it will go to 0 much faster than the slow mode. So that is the key idea to approximate the higher order system by lower order one. So the simplest approximation, right, is just to say, okay, this is the third order system. I just throw away the fast mode, only keep the slow mode. But if you look at this expression, you may notice that I not only throw away the fast mode, I also change the numerator from 2 to 1. So why do I need to change the numerator? I know some people say the why, but why? What do you mean by why? Why do I need to change the numerator from 2 to 1? Any suggestion? How do how do you get the state desecant of a system? If you have a transfer function, how do you get the desecant? You will set S equals which value? 0, right? When you try to make those two transfer functions match, right, or approximate, of course, the desecant has to be the same. If you compute the desecant for the original system, of course, the desecant is 1, right? You put S equals 0, will be 2 by 2 will be 1. Then for this one, if you don't change the numerator, right, the desecant will be 2. That's why I have to use 1, such that the desecant match each other. Okay. Okay. Then let's do the simulations. How good is approximation? Of course, you don't expect a perfect match of the state response. There must be some difference. But overall, you can say it is quite good, right? There is some difference at the beginning, but after a while, the response of the two systems are very close. Of course, the desecant will be the same, right? The steady state value, both of them go to 1. Okay, so this is just an example for you to know, okay, how we're going to approximate the higher order system. Okay, in the following, I give you just one example to show why do we need to do the power placement. Of course, this is a diesel motor position control. If you have a motor, right, if you apply a voltage to that motor, you expect the motor will rotate, right? But sometimes, right, you want to control the position of the motor, and then you have to build a control system to do that. Here, I just show you the toy example built by students in the lab. Anyway, I will skip the modeling part, but those are the parameters. But you know, this one can be, the model can be for motor, right? We have the perfect knowledge. So we build the model. The first one, that is the Newton's second law. The second one, right, is from the Kirchhoff's law. Okay, and then we have this system theta is the position of the shaft of the motor. Input is the voltage. If you look at the equation of this system, here is the second order differential equation, right? Here is the first order differential equation. If you look at the equation of this system, is this in the standard state space model form? Is this in the form of x dot equals ax plus bu? No, right? No. So if you look at this equation, what are the state variables we can identify? What are the state variables? Position, theta, the current I. How about the other one? How many state variables do you expect? There are 3, right? What is the third one? The speed, right? Theta dot. Remember, how can you get the state space model for a second order system? You include the theta and also the first order derivative. Okay, so therefore, we have to write it in this form such that we can use our approach. We have to write it using the state space form. Okay, that will bring us advantage to give you the general solution. We don't deal with the other form. Okay, all our control theory here in this course were built upon the state space form, which you have learned in the first part. X star equals AX plus BU. Of course, here is X, right? X star, or X is theta, theta dot, and I, three state variables. So this is A, right? A times X, and then this is B. This is B. The voltage is the input, right? You change the voltage, you will change the state, and then the output is just the position, theta. Okay, let's say we have to give some performance requirements. Right? Without that, we can't design the controller. For this one, let's give two performance requirements. Let's say the settling time, we want it to be 40 milliseconds, and the overshoot we want to be less than 16%. Okay, now without feedback, this is the open loop response. If we apply a step input, which means if you apply a constant voltage, this is what's happening, right? Just as the motor will rotate forever without any feedback. Of course, we say this is not what we want. Why? The system is unstable. We want it to have a certain settling time, right? It should finally settle down to some value, right? And then the settling time and the overshoot has been specified. Okay, we need to put a feedback control. We have to change the pose to some desired one. Okay, now let's sum up with the rational power placement, right? We want to meet the performance requirements, right? We build our reference model, and the poles of the original system, of course, are not the desired one. We want to change them to the poles of the reference model. And of course, the poles are the critical property for the dynamic system. If we want to match the reference model, we want to match the poles. Then there are two questions. Is power placement possible? Then how can it be done? You are going to learn that today. Let's first get the solution for the single input case. Single input, which means, right, the input is just a scalar. So therefore, the B is no longer a matrix. B is just a vector, a column vector. Then in this case, your gain matrix will become a vector. K will be the gain is a vector. The K is our column vector. Of course, then we do the transpose such that this we have a row vector times the column vector, right? We get a one number scalar. Okay, so also if we write in this form, just says that the input is just a linear combination of the state variables. Okay, then for the single input, single output system, right? Let's say we already know the desired position of the poles. So how did we get that? We already mentioned, right? You design that, right, to meet the performance requirement. So therefore, when we try to solve the pole placement, we already know what are the desired poles, right? This one, right, from the performance requirements. So therefore, we know the desired poles, which means we also know the characteristic polynomial of the desired system. This corresponds to the denominator of the transfer function of the reference model. Okay. Okay, so what is the mathematical problem? We want to design the K, the closed loop system, right? This matrix. After this is the matrix for the closed loop, well, which will depend upon the K, such that this is the correct polynomial. of this closed loop match the desired polynomial. Okay. For pole placement, remember, if we make those two polynomials match each other, it means the poles are the same. Right? Okay. So of course, how are we going to match them? Well, how are we going to match them? We'll have to match all the coefficients of that polynomial. Okay, then let's state the first theorem. We say if the system is controllable, then we can do it. And then we're going to show you how to do that and how we derive the formula. Okay, let's say if the system is controllable, right? AB is controllable, we can transform it into controllable canonic form. This is what you have learned in part 1. It means that we know there exists a transformation T, and we also know how to compute that transformation. Okay, T, and then this is the original state, right? This X bar is the state vector for the controllable canonic form. This is original state space model. So after transformation, we can get the state space model for the canonic form X bar dot, right, equals T times X dot, right, we plug it in. So eventually we have this one, right? This A bar and A are related by the transformation matrix T. And also B bar is related, right, to B by the transformation matrix T. Okay. Now here, because you just learned that, right, in the first part, I hope you still remember the form, mathematical form of the controllable canonic form. Do you still remember? I hope you can. Is this the form you have learned? Controllable canonic form, right? Controllable canonic form. Okay, let me just explain those parameters again. Here, the last row, right? The last row of the controllable canonic form, we call this row as a non-trivial row. The numbers are corresponding to the coefficients of the Caractère polynomial. For any system, you have the Caractère polynomial, right? This is the definition of the Caractère polynomial. Of course, that corresponds to the denominator of the transfer function. If you know that, then you get those coefficients that correspond to the rows, right? The last row, the nth row of the canonic form. Then how about other rows? The first and the second to the n-1 row, the numbers are completely fixed for any controllable canonic form, right? For different systems, they have the same, they will have the same numbers. They only differ in the last row. That's why we call those rows as the trivial rows. Why it is trivial? Because the numbers are completely fixed for any system. Different systems only differ in the last row. Another important part, of course, is this vector B. This vector B is a unit vector, but the non-zero value, right, also corresponding to the last element of this vector. But all the other values will be 0. Okay. Now, let me explain why this one, right, can make the controller design a very easy task. Let's just show the graphic representation of this controllable canonic form. Here, you see, when we look at the equation, right, the first equation just says x1 dot equals x2, right? The first equation, x1 dot equals x2. It just means x1 is affected by x2, right? I use a graph to show. Now, how about x2? x2 dot equals x3, right? So we say x2 will be affected by x3. x3 will be affected by x4 only. But how about the last state variable, xn? We can say, okay, the xn dot will be affected by all the other state variables from x1, x2 to xn, right? So that's the meaning of this graph. We show xn will be affected by x1, x2, x3, and also affected by itself. And also importantly, it will be affected by the input, u. And also from this graph, we show the input u does not affect the other state variables directly, okay? But those state variables are connected by a very special way. So the input only affects the one state variable, but the state variables are related to each other in a very special way, such that, right, if the xn is controlled properly, all the other state variables will behave properly. Okay, so therefore the problem becomes using one input to control one variable. That makes it much easier. So you can see that's the reason in this input vector here, you can say that the input only affects the xn, right? The input does not affect the other variables directly. Okay. Now let's say how we can first solve the problem, the power placement problem for the controllable canonic form. Okay. So let's just do that analysis. Let's plug in, right, the expression of the term p bar times the k bar transpose, right? Here is the p bar, that is the control vector for the controllable canonic form is a unit vector with all the values of 0 except the last item is 1, right, times this row vector. Because of this special form, we do the multiplication, then we get a matrix, M matrix, also with a very special form that all the rows are completely 0 except the last row. The last row, right, will be affected by the gains. Okay. Okay. I think, right, probably at the first class, you may not familiar with how we're going to do the matrix and metric calculation. Now it's the 7th week. You should know how do you do the calculation of the product of the vector and the. Okay, you should not have any problem. If you have any problems, you will be in trouble. Now in this one, you can say that, okay, it just means that the input only affects the last state variable, right? Because the other values are completely 0. And if we put them together, this is the matrix after the feedback and takes this form. You just pay close attention to this form. And then tell me, is this form still in the controllable canonic form? Actually, it is, right? That is the key. That is the key that the control input only affects the non-trivial row, right? The trivial rows are still the same because the trivial rows don't change by the feedback gain. That makes the calculation of the correct polynomial very simple. Okay. All the numbers, right, in the actually here the another property is that all the numbers in the non-trivial row can be changed independently, right? The first number here can be changed by K1. The second number can be changed by K2. Okay, that is the best part of the controllable candidate form. This was introduced specifically to solve the pole placement problem. Okay? Because once you are here and you know it is still in the controllable canonic form, so when a system is in the controllable canonic form, how do you get the correct polynomial? You get the numbers from the non-trivial row, right? The last two rows. You just take those numbers and you know those numbers correspond to the coefficients of the correct polynomial. Right? The correct polynomial of the closed loop system will just be like this. Okay? Any questions? Okay, here, this is where we are. We know this is the correct polynomial of the closed loop, right, with the state feedback for the controllable canonic form. And it has a very nice property that each coefficient, right, can be changed by one gain separately, right? Independently, they can be changed by the control parameters. Therefore, if we compare it to the desired correct polynomial, if you are given any desired correct polynomial, then you can say, I just try to match the coefficients, right? We have n coefficients to match. It should be clear to you how we're going to match that, right? Very easily. If you match those two, right, you get the difference will be gamma minus alpha 0, right? If you match those two, you can easily match all of them, right? Just design the gains. Okay. I already tell you how to do that. Of course, it should be obvious to you. Therefore, you say just match those coefficients and then I design again of the controller, right? Those gains actually just the difference of the coefficients, right? Difference between the desired one and the actual one. So in the ideal case, if the actual one already match the desired one, of course, right? You can say if gamma equals alpha, the gain will be 0, right? You don't need to change anything. So we have a very simple solution for the pole placement for the controllable canonic form, right? And then we try then you say, how about the controller for the original system? Because we know T, we know the transformation matrix T. So we can easily get the solution, right? We already know how you get the K bar, right? Just multiply by T, then this is the gain for the original system, right? Will be K bar transpose times T. Okay, and then, right, the mathematicians have gone further. They show, okay, you don't have to do this, right? Eventually, this is the formula. You can apply. Well, this is just a raw vector, right? This is C is the controllability matrix You have learned. And 5D is the desired correct polynomial. When we put 5DA, it means that I said S equals A, right? And that I compute its value. Then you get this one. This is what we call Eichmann's formula. Okay, so we don't have time to prove that, right? If you're interested, you can check the textbook. But it's related to the Cayley-Hamilton theory, right? You have already learned that in part one. One of the most important theories for linear system. Okay, so let's summarize. How we're going to compute the K for the power placement problem for the single input case, right? Given a controllable pair of A, B, you are given that, and then you have a stable 5D, the desired polynomial. You want to find the gain such that the correct polynomial of the closed loop match the desired one. You can use Eichmann's formula. Okay. Now, so what if you forget this Eichmann's formula? Of course, in your final exam, of course, you can bring your data sheet up. Even if you forget, you can just look at your data sheet and say, what? Okay. But if you don't use Eichmann's formula, there is another way. I will call the direct comparison, such that you don't even have to remember. You don't even have to put the Eichmann's formula in the data sheet. In your final exam, it's close to the exam, right? But you are allowed to bring you one A4 size data sheet, right? You can put all the formulas there. So if you want to save space, you say, I don't want to put the Eichmann's formula to save space. There's another way. You can do it. Here I'll go to show you. It's also very easy to understand. Okay, for this system, right? This is A, this is B. We say I want to place the post, right? Now, of course, you know this one. The two eigenvalues are 0, right? Of course, it's a double integrator. You don't want, okay, you want to make it stable, so you want to put the post to -1, -2. You want to solve this problem. How can you design the K? You just, right, you say, okay, this is the controller you're going to use, a state feedback. You want to find out K1 and K2. You just plug this in to your system, you get a closed loop. Right, this is A, this is B, this is K. You do the calculation, okay? Of course, you should be familiar with this calculation and how to do that. Okay, you do this, you create this one is the polynomial, closed loop polynomial, closed loop matrix, and then you try to get the closed loop correct polynomial for this one. Okay. Of course, also you notice actually because it is in the controllable kinetic form. You say the correct polynomial is you can just take out those two numbers. Those long trivial row get K1, K2. Right? On the other hand, right, this is the desired one. S+1 and S+2, you have those two stable poles, right? Okay, and then you try to match. Clearly, you can see the answer, right? K2 has to match 3, K1 match 2. So you can say in this way, you didn't use Eichmann's formula. What you did, right? You should know how to get the correct polynomial of a matrix. If you know that, then you end up with a polynomial of your closed loop system, right? And then you make it match the desired one. You have two equations, right? Or in this case, then you get the answer. So this is also a very simple way. But this way, if you do it, you may notice that if the system order is 3 or higher, there are some issues there. Okay. Therefore, another example I want to show you how to solve the problem with the Eichmann's formula. Okay, here we say that this is Eichmann's formula. Now let's solve it. Then we have this one. We say, okay, this is the system. This is A, and this is B. And then this one we say, I want to place the pose to -3 and -4. We get the desired polynomial. Get this one. Once you get the desired polynomial here, I want to show you, okay, how do you evaluate this? When the desired polynomial, when you put S equals A, what does that mean? Because here is A, right? A squared, of course, you multiply those two matrices. 7 times A is the common mistake, right, made by the students in the past is the last term, right? This is the 12 times the identity matrix. Okay, in the past, when students do the simulation, imagine that the mistake is just they don't multiply by identity matrix. They imagine that they just plus 12. Okay, if you plus 12, this 12 will be added to every element. Okay, so that is the mistake. Don't. So here, that's why I want to show this one. This is identity matrix. Okay, then you do this calculation, and then finally, okay, this is the way you compare to this part. So this is C, right? Then you need to know the definition of the controllability matrix. And then you get the inverse of this matrix. So finally, you use the Eichmann's formula, right? 0, 1 times C inverse times this phi d of A. So this one does not involve any solution to a set of ordinary equation, but it involves the matrix calculation. Okay. Let's summarize what I've discussed so far. So what is the condition for solve the power placement problem? There is one condition, right? What is the condition? The system has to be controllable. If the system is not controllable, you don't have the controllable canonic form, right? Okay. How many solutions can you get? There's only one solution. That solution is given by the Eichmann's formula. Of course, Eichmann's formula only gives you one solution. That is the only one you can get. How many methods you have learned so far? You have learned 2, right? You can do the direct comparison or use the Eichmann's formula. Which one to choose? Okay, the direct comparison is simple when the order of the system is low, 1 or 2, but Eichmann's formula can be applied to any dimension. Okay. So with that, I will call a break. So let's have a break. 50 minutes break, then we will move on to the next part. So during the break, we'll play some video, and of course, you are free to leave. All right, welcome back. So just a few words on the files I uploaded in Canvas, right? I already uploaded the lecture notes. Okay, but remember, I don't have time to cover all the topics in the lecture notes, so I will leave some out. In my lectures right here, like this one, you will notice what I'm talking about, right? I'm not the same as the lecture notes. So the lecture notes is for you to read. So I select the most important ones to discuss in the class. Okay, so in the class, of course, I give you more details to explain those concepts and ideas in the lecture notes. And the PowerPoint slides, of course, will be released after the class. Okay, will give to you. You also have that one, so those two will complement each other. And then there is another set of files called tutorials, right? Tutorials basically I give you the questions and the solutions. Those ones you have to study them by yourself. Okay, we don't have time to have conduct a separate tutorial class. So for that one, I think you know what is the effective way to read those tutorials. The effective way is you should work out the answers by yourself, right? And then you check the solutions. So whether you get the same answer or course the method may be different, right? And then you will know that. You know, don't just read the solutions directly, right? In that way, you will learn very little because you don't know whether you can work out the solutions by yourself or not. Okay? Now let's move on to the next part. Okay, for power placement, let's recall what should we do? How do we design the desired ones? Right, we use the performance requirements. First, to determine the pair of the dominant poles, we use the second order system, right, to guide us. We know the properties of a second order system from the requirements on the settling time, the overshoot. We can figure out what are the proper values of the pair of the complex poles, right? We get those, and then, for example, here I just say if the complex poles will be like this, right? And then we know the decay functions. We look at the real part, e to the minus 2t. We need to know that because that one will give us some idea of how do we design the extra poles. Why do we need the extra poles, right? Because in the reality, the order of the real system may be higher than the order of your reference model, so you have to design the other poles, right? Extra poles, we want to be faster than the dominant ones, right? Because that's the way we approximate the higher order system. So normally we say that's 2 to 5 times faster. Like if the dominant mode is e to the minus 2t, so we say the real one, if it's 5 times, I want to set it as minus 10. Then, of course, that will not be the final design. You may have to change the pose, location, right? You run the simulation, you find out whether by placing the pose to those desired ones, it may not satisfy the requirements because the final outcome of the step response, right, not only depends upon the pose, it also depends upon the zeros. So you have to do some more experiments to fine tune the location of the pose. Now let's go back to the DC motor example, right? This is the state space model. We know this is a control requirement. So we say, okay, we know the settling time and overshoot ratio. Okay, now for this one, how many poles should we design? It's a third order system, right? That's supposed to be 3 poles. Okay, then you first design the 2 dominant poles. Those from their design requirements, we know the settling time, right? We know the overshoot. So therefore, we know the requirement on the damping ratio and lateral frequency. They have to satisfy this inequality. Then we first settle the damping ratio. Okay, then we set this number, and then we also want some simple number. We get those zeta omega n equals 100. Okay, this way actually we put those specific ones such that it can make the calculation easy. So actually, the correct polynomial for the prototype of second order system will just be like this. Okay, then there is a third pole we have to choose. Then you look at this one, right? Because this one is minus 100. So we want to choose the third pole should be 2 to 5 times faster than the dominant one. Then we can choose lambda as minus 200, just 2 times faster. Is that clear? Okay. So finally, this is the correct polynomial we want to match. This is the desired one. Okay, with that one, once you know this one, then you just apply the itemized formula, we will get the design. Then we can compare the difference between the open loop control, right, and the closed loop. The step response, when we apply step input, we know the open loop is unstable. Now the closed loop, right, the closed loop, of course, is stable. And if we look at the performance requirements, we want the settling time to be less than 40 milliseconds. Here is 40 milliseconds. The settling time will satisfy the requirement. Overshoot, of course, is well below 60%. But of course, you may notice that the state gain is not 1, right? It's not 1. So right now, we only try to satisfy those two requirements. So we didn't set the requirements on the final state value. Okay. To meet that goal, we will discuss how to do that, right? Okay, in chapter in week 9. But for those two requirements, we already meet. Now let's move on to the case where we have multiple inputs, right? This is the part which makes the difference between this module and the other one on computer control. We did talk about how we deal with the multiple input one. Now for this course, we do have the solution for the multiple input case. So here, let's say there is not just one input, right? There are more than one input. So there are 2 or more. How are we going to solve the problem? Still, we say, of course, we just change the n is no longer a vector, will be a matrix K. Okay, then we just plug into the closed loop. So the closed loop system becomes A minus BK times X. So how this K will affect the poles of the closed loop? Then we say, okay, the pole placement problem, right, we have the desired correct polynomial. We want to design again K such that this closed loop system, right, that the correct polynomial of this matrix A minus BK match the desired one. Okay. The question is how we're going to design K. Okay, let's first try the direct comparison method. And then you will know there is a big difference between the solution of the multiple input case to the single input case. Let's try a very simple one. We say, okay, this actually is already in the controllable canonic form, you may notice. But now I have 2 inputs. I have 2 inputs. Okay, then we say, okay, this is the desired polynomial which ought to match. Let's check whether the system is controllable or not. For the multiple input case, this is the way we get the controllability matrix. You can say it is no longer a square matrix because we have multiple input vector, right? But we know it is 4 rank, so therefore it is controllable. Then let's just move on. Let's just do the direct comparison, means that we're just plugging the expression of this game matrix, right? K, we directly plug it in. So this is A minus BK. So this is A, this is B times K, because B is just the identity matrix. Then we get this one, right? And then we get try to get the determinant of this matrix. Okay, then finally, this is what we have. That will be the correct polynomial of this closed loop, right? And then we compare with the desired correct polynomial. This is the desired x squared plus 2s plus 2. So this polynomial should match this one. We match the 2 coefficients. We have the set of equations to solve. But you look at this, because we have two coefficients to match. So how many equations do we have? We have two, right? Now how many design parameters we want to get? We have four. Then how many solutions can you find? How many? Infinity, right? Infinity. I know many of you don't like the too many solutions, right? Okay. But recall what we just solved the problem for the single input case. How many solutions can you find? There is only one. Okay, since we already know how to do this for the single input case, then let's ask the question, is it possible to convert the multiple input into single input system? Multiple input means that you can choose multiple input signals at the same time, right? But can we limit our choice to only one input signal instead of multiple? Can we do that? Of course, right? Who designed the controller? You. You guys can decide, right? Which control signal you want to use? Answer yes. Because you can choose whatever input you want to apply. Therefore, what is the simplest way to force the multiple input to single input? You just put one input, right? And keep other input signals at 0. You don't use the other ones, right? Just use one. Right? Okay. So, but there's some other ways. We say, okay, yes, you say, I'm going to use all of them, but we set all of them to be the same value. Okay. And you say, hey, no, I want to put different weights, right? So I design a weight vector. So I first design this Q1, Q2, right? This vector. And then I just want to, okay, we will fix this Q. And then this V is just a scalar. There is only one signal we want to choose at the end. So anyway, so over this basis, the purpose is just try to force the multiple input into just one input. The reason you say, because I know how to do it for one input, right? I want to make it simple. Okay, fine. Okay, then we say, what happens if we do that? We say, let's look at the equation. We say this U, right? Input becomes this weight vector times a scalar, one number. If we merge those P times Q, right, that will be just one vector. This V is just one number. So if you just look at this system, is it a single input system now? If we put the V as the input, of course, there is only one input. So that is the way we can force the multiple input into a single input. And for single input, you know how to do it, right? So we convert the multiple input to single input. Okay. And then, okay, you say, okay, then I just follow whatever you have learned. But in the first half, you design this K. So overall, of course, the controller will be Q times V, right? We plug it in. This is the V, and this is the Q. So therefore, the final gain matrix will be K. K is just this Q, right, times the V. You look at this matrix. What is the rank of this matrix? What is the rank? Come on. Remember what you have learned in the linear algebra. If you have two matrices, you multiply them together, that is the rank of the total cannot be bigger than any one of them, right? Let's say, what is the rank of Q? What is the rank of Q? Of course, 1. You have only one vector, right? What is the rank of K? Of course, 1, right? So therefore, the total rank is 1. That's what we call the unit rank method, right? This one is simple. Okay, let's try. Let's try one example. And let's first be very clear about the procedure. You first choose the weight vector such that A, right? Then this B times Q is a vector, right? This BQ is controllable. Of course, you have to satisfy that. Then you use the single input power placement algorithm to compute the K, the given vector. Okay. The overall, this will be your feedback matrix. Q times K transpose. Let's look at one example here. Okay. A very simple example. Okay, and then those are the two poles, right? Those are the desired one. You get the desired correct polynomial. Of course, let's just follow the steps, right? It is controllable, of course, because B, right? This one itself is already a 4 rank one. Okay, and then you set Q here. I just design my Q as 0 and 1, but essentially means that I only use one input. Okay, and then you say, okay, this is B times Q, right? Then of course this one will be 4 rank. This BQ is controllable. Then you set your K1, K2. You plug it in. You get the correct polynomial of the closed loop we match with the desired one. Then you get your K1 and K2, right? And then you get your given matrix is Q. This Q times the K1, K2. That will be the solution. Okay. But you look at all the steps. Is there a solution you need? There could be other ways, right? If we choose another weight vector, this time I'm going to use both of them, right? With the same value. Then you will say what happens. They will say B times Q will be 1, 1. Previously is 0, 1, right? Then there's a difference. And then we'll get this 4 rank and do this again. Okay, do this again. So eventually you get this solution. K, the K will be 2, 0. Okay, the final answer will be, because this is 1, 1, but this answer is different from the previous one. Okay, you can say there are multiple answers. So, and also now, you also know why. Why do we have multiple answers? Because the weight vector, right, the infinite number of ways to set the weight vector. But again, we don't have too many choices, right? And also, when we do this, we say, hey, we have many inputs. Why do you want to limit to one input? Right? We lose the power of the multiple input. We should fully explore the advantage of multiple inputs. Okay? So now we say, hey, look, I want to use all the input independently. How are we going to do that? Okay, let's try to discuss the way we are going to solve it, right? But with more efficiently using all the input signals. Then we have to recall, how did we solve the power placement problem for the single input case? We show that the controllable canonic form is the key for the solution, right? We use this controllable canonic form to get the solution, okay? Then we ask ourselves, can we also rely on the controllable canonic form for multiple input case? But how do we obtain the controllable canonic form for multiple input system? Okay. We will go through one example for you to have an idea about the algorithm or about the whole procedure. Let's look at this one. We have a third order system, right? There are two input. There are two outputs. Okay, then let's first discuss what is the controllable canonic form for multiple input system. Okay, how do we go to obtain the controllable canonic form? Okay, first, we compute the controllability matrix. This one is well known, it's given in the part 1, right? You do this one, the difference is that B will be a matrix, right? Is no longer a vector. If we write down the whole form, okay, the dimension, right? How many vectors is no longer an n vector, right? There are n times n because there are n input, right? If we do this, there will be n times n vectors in this matrix. You check whether it is full rank or not, right? If it is controllable, which means it is full rank, then you move on to the next step. If it is not full rank, well, we know there is no solution. Okay, so we know it is full rank, which means you can select n independent vectors from this matrix, right? Because it is full rank. For single input system, of course, we know there are only n vectors, right? This controllability matrix is a square matrix. If it is controllable, right, all the vectors will be independent. There are n vectors. Here, there are m times n vectors, right? And also we know, of course, we can select n independent vectors from this whole set. But there are many ways to select those n independent vectors out of n times n, right? So therefore, let's just follow one way. In this way, you can only get one possible set of n independent vectors because we are going to select the vectors. We have this matrix, right? We're going to select them one by one, strictly from left to right. So you first check B1 to Bn, and then you check A times B1 to A times Bn. Okay? So only if you cannot find the independent ones, right? And then you move on to the next one, strictly from left to right. In this way, you will get one set of n independent vectors. Okay? Now, the next step, right now we have a square matrix. Now here, you group them into a square matrix in the following form. This matrix C, you get the n independent vectors, right? But now you want to put them into this form. Remember, there is a difference in the form between this one and this one. This one, right, is grouped by the power of A, right here. There is no A. This one, right, there is only one A, right? Here, we group them in terms of the control vector, B1. So you see, the first D1 vectors are all associated with B1. Then the second, right, those group of vectors associated with B2. So we are going to arrange their matrix in this form. Okay? Any questions? Okay. This one is a critical step. If you get this wrong, all the rest will be wrong. Okay? If you put the vectors into a different sequence, right, into this matrix C, of course, you will get different answer. But that way may not give you the correct answer. So up to now, we only have one solution. You have this one, WC. To get this matrix, square matrix C, there is only one solution. Okay, you get that one. Okay, and we know, of course, this is a square matrix. It is full rank. You can get the inverse of that. Now, let's just look at this example and say, what does that mean, right? In terms of the procedure, you get those WC. There are, you can say it is not a square matrix because we have two inputs, right? So therefore, there are 6 vectors, okay? And we know it is 4 rank, so we are going to select 3 independent vectors. Now we say, how we're going to select them? This is an important step, right? What do we mean by selecting them from strictly from left to right? You first, of course, this one, you know, of course, you get the second one. This one is clearly independent from the first one, right? You get that. Now you try to look at this one. Then you notice this one, right, is not independent from the second one. So then, okay, you are not going to select it. You move on to this one, right? Okay, so that is the way we get those 3 vectors are this one, and this one. Okay, there is only one possible solution. If you don't follow this order, of course, you say, I don't select this one. How about I get this one? Of course, you can say those 3 vectors are also independent, but that is not the way. We have to follow the order strictly from left to right. You cannot jump, or you cannot jump this one. Okay, is that clear? In this way, we'll get one solution. Okay, and then, but when we try to group them, of course, this is clear because it's already in this form, right? This is B1, this is B2, and then this one is already A times B2. This one, right, is related to the first input. This second one, third one are related to the second input. Okay, so now we get the matrix C. Any questions on how to construct the matrix C? Okay, now then the rest we have a fixed procedure to get the other matrices. Okay, the first one is how we get the transformation matrix T. For multiple input case, we have to specifically compute the matrix T. Without T, we cannot get the controllable kinetic form. Okay, we have to compute the matrix T. In order to do that, well, we need to compute the inverse of this matrix C. This C is already given, so we get the inverse of that. Okay, let's look at this matrix row by row. There are n row vectors in that matrix. Then we first understand how do we get the transformation matrix T for the single input case. Then this one can be done, can be obtained from this inverse of this matrix. There are some other ways to get T, but okay, that the other ways are not important. We have to follow this way. Today I'm going to show this way. Okay, the reason I just show you why we construct the T in a very special way. You just look at those 2 matrices, right? The inverse of the C times C. Okay, this is the inverse of C. This is the C for the single input case. For single input case, the C, of course, is the controllability matrix, right? Then we do the multiplication, right? We know this, of course, it should be our identity matrix. Then we just look at the last row. The last row, we take out the last row of this matrix. We get those Q and transpose that corresponding to the last row of the inverse of C. So we say, okay, this one will give you a unit vector, but then if we just construct the T in this form, then those T times B are those values here. T times B are equal, you will notice, well, I already give you this value that corresponding to T times B. I just write into a column vector that corresponds 0, 0, 0. The last element is 1. This vector, control vector that corresponds to the vector in the controllable canonic form. So this is the reason we can construct the T in this way. Okay, that is for the single input case. Any questions? So we don't have time to prove all the mathematical steps. Right now, I just give you the computational procedure. All right. Now, when we construct the T, so we only take out the last row of this matrix, the inverse of C. The reason because there is only one input. For multiple inputs, actually, if we want all the inputs to be applied to the system effectively, right, we need to take out more rows. Not just one row. One input corresponding to one row. You have two inputs, you have to take out 2 rows. You have multiple inputs, m inputs, you have to take out n rows of this matrix. Okay, this one will be the, I just give you the formula for you to construct this T. You can see there are n inputs. Okay, so that's why you need to take out the n rows from this matrix C inverse. And if you look at this, okay, the first input, right? The first input, then you say, okay, which row are you going to take out? What is D1? D1 corresponding to the number of the input vectors which are related to the first input. So therefore, you first have to know the form of this matrix C. You look, okay, how many input vectors are there in C? For the first input, you get D1. Once you know D1, which this one means that will be the dth row of this matrix C inverse. Okay, that's the meaning of this formula. Okay, then the second one, which row are we going to take out corresponding to the second input? Then you look at how many vectors are there in this matrix C are related to the second input. So you say if there are D2 of them, then you take out the D1 plus D2 row of this matrix C inverse. That's the meaning of this formula. Okay, you take out the row, of course, then also you have to multiply by the matrix, right? This one, therefore, here there are 1 row, then how many rows are related to the first input? You compute, there are n rows. There are D1 rows in this matrix T, and then there are D2 rows corresponding to the second input for the matrix T. Okay, in this way, you can construct transformation matrix. Okay, any questions? So once you have this one, then actually you can show the main point is you have this construct transformation matrix, right? If this transformation matrix times the original input matrix, will give you the input matrix for the controllable canonic form. The interesting property of this matrix is only this row, those are the non-trivial rows, right? They can affect the system. All the other rows are 0, but there are n of them. There are n rows. So this one is the rows which can affect the system. All the others are 0. For the single input case, we know, right? We know there's only one row will be 1 because we have only one input. Here we have multiple inputs, so therefore there are multiple non-zero rows in this matrix. I want to use all of them, not just one. Okay. Now, all right, let's just look at the example. Let's go through this example, and then you'll know. And also, there's some other examples in my tutorials, right? You can try to follow that, right? And then you understand the procedure. For this case, let's see how we're going to do that. We already know the C and matrix C we construct from the controllability matrix. We select them, 3 of them, strictly from left to right. I already showed you how to do that. Then you get the inverse of C, right? Inverse of C. So therefore, you need to know how to get the inverse of a 3 by 3 matrix. Okay. Then we have to decide. We know we need to select 2 rows to construct a T because there are 2 inputs, right? So if you look at the form of this matrix C, how many vectors are related to B1 or related to the input, the first input? How many vectors are related to B1? There is only 1, which means, right? Which means D1 equals 1. What does that mean? Which row should we take out from this matrix C inverse? Which row? Because D1 equals 1, which row should we take out? The first row, right? The first row. Then how many vectors are C associated with the second input? How many are related to D2? There are 2, right? So we say D2 equals 2. D1, D2 are the numbers of the vectors are related to the input. Then, which row should we take out from T? We say the first one is the D1's row. The second should be the D1 plus D2's row. But if we go back to this is the formula, right? This is the way we use. The first we take out the D1's row. The second one should be the D1 plus D2. Okay. So therefore, the first row, right, D1, and then D1 plus D2. 1 plus 2 not should be the third row, right? D1 equals 1, so therefore there is only 1 vector related to the first one. D2 equals 2, there will be 2 vectors, right? Q3, the third row, and then there is another one, Q3 times A. Okay, this way, you get out this one, Q1, the first row, and then this is the third row, and the last one is just this row. Okay, any questions? So this step is also important. If you make a mistake in constructing T, of course, the rest will be wrong, right? Okay, so here, C, there is only 1 solution to get the C. Of course, you get the C, you get the inverse of the C. There is only 1 solution. When you construct the T, of course, there is only 1 solution to construct T. You have T, you have to get the inverse of T. And then you can compute the controllable kinetic form. Now you look at this controllable canonic form. You realize, right, this is totally different from the controllable canonic form for the single input case, right? Because for the single input case, this is supposed to be 0, 1, right? The first two rows are supposed to be the trivial row. Only the last row are the non-trivial row. But here, look, the second row is the trivial row. There are two non-trivial rows. If you look at this matrix, B, those two are non-zero. Those are the non-trivial ones. They can affect the state variables, but they corresponding to the position of those two, of course, corresponding to the non-trivial rows of those controllability, the canonic form. Okay, there is a big difference between the canonic form of the single input and the multiple input, because we have multiple inputs. Therefore, we have multiple non-trivial rows. Each input will affect one of the non-trivial rows. For single input, we have only one input. Therefore, there is only one non-trivial row. Is that clear? Okay, I already explained that. Now tell me the answer. How many non-trivial rows are there in the canonic form? 2, right? Because there are 2 inputs. Okay, now you design the feedback gain matrix for the controllable canonic form. Okay, you say you're going to design the feedback gain matrix K bar, right? There are 6 numbers to design. Then you form the closed loop matrix, which means you compute A bar minus B bar is here times K bar. Because of the special way you arrange those K bar and B bar, you will notice, right, the combined closed loop matrix, the gain will change the non-trivial row. How about the trivial row? Is the trivial row the same as the A bar? The trivial row does not change. That's the key point. The input will not affect the trivial row. It only affects the non-trivial row. Okay? Is that clear? Therefore, after the feedback, if you look at this matrix, is it still in the canonic form? Is this still in the canonic form? It is, because the trivial rows are the same as the previous one, right? Only the non-trivial rows have been changed. And all the numbers, there are 6 numbers, right, in those non-trivial rows. There are 6 numbers in the design matrix. Okay? Now, so therefore, the critical point, right, or the beauty of the controllable canonic form is that the feedback will not affect the structure of the canonic form. Okay, so it is still in the form of canonic form. Therefore, we can easily match the canonic form with the desired one. We can get the solution. But then we have to know what is the desired canonic form. Remember, this is the canonic form. We know that the trivial row is in the second row. Actually, the trivial row should be 0, 0, 1. I don't care about the other 2 rows. Those are the non-trivial rows. Okay, so we need to design a matrix which have the same trivial row, the middle one, the second row, 0, 0, 1. Okay, the other 2 rows we have to design the numbers, but we design those numbers such that they have the desired eigenvalue. The poles are the -1, -2, -3. Okay, you first get the desired correct polynomial, right? Because it's -1, -2, -3, so we get those s plus 1 times s plus 2 times s plus 3. But then I can put it as a one polynomial, a first factor, and then there's a second polynomial, a quadratic form. Okay. And then a possible desired closed matrix will be like this. You can consider this kind of there are two blocks to design a submatrix. The first one has an eigenvalue -1. The second matrix, you only look at this matrix, 2 by 2 matrix that corresponds to this one, will give you this desired polynomial. Okay, so therefore, the total eigenvalues, right, of this matrix will correspond to the roots of this polynomial. Yes, please. This one has a eigenvalue, right? This is the correct polynomial is -1, so I put -1. This one, if I only look at this one, second order, so I look at this matrix. That is the canonic form for a second order system where you have this correct polynomial, right? The first constant is 6, 5, so get -6, -5. That's one way we construct this matrix. And we know, okay, we know this matrix its corresponding correct polynomial will be in this form. Is that clear? Okay. And also, importantly, if we look at this matrix, you look at this second row, it is in the form we like. We want to be 0, 0, 1, right? That is canonic form we designed previously. Okay. Once you know, okay, this is the desired matrix we want to match, then you compare this is the closed loop matrix. This is the desired matrix. We already matched, right? The middle one, the trivial row, right? Then you try to match all those 6 numbers. We have 6 equations. You have 6 unknowns, right? Then you can easily get those 6 numbers. But this is the solution for the canonic form. So the final solution will be this k bar times t. Then you have this matrix. That will be the game matrix if you follow this design. If you look at the rank of this matrix, what is the rank of this matrix? What is the rank of this matrix K? 2, of course, right? It is 4 ranked, so that's why we call this is a 4 rank method, which you exploit all the inputs. You want to apply all the inputs, okay? Independently, you don't want to force them into one single input case. All right, any questions on the design procedure? Clear? Then let's just summarize the algorithm. I just show you, okay? The algorithm for the 4 rank placement, you are given A and B. Okay, B is no longer a vector, it is a matrix. Also, you are given the desired correct polynomial. You first try to obtain the controllable canonic form. Okay. This will be the most time-consuming part to compute T, that transformation matrix. That takes many steps. In order to do that, right, this controllable canonic form will depend upon the square matrix C formed by the n independent vectors from the controllability matrix. And then you have to get the inverse of that matrix. First, need to get this right. Okay. Also notice I want to emphasize again, right, the sequence of these vectors are different from the sequence of the vectors in the original controllability matrix. Once you have those T, then you can get the controllable canonic form. This controllable canonic form is different from the controllable canonic form for the single input case. You will have multiple long trivial rows. Okay. Then you have to design a desired closed loop matrix, AD, okay, such that, right, those AD will have the same pose as the desired one, but also the AD is in the constructible canonic form such that, right, the trivial rows of those AD should be the same as the controllable canonic form of the original system. You make sure of that. Then you compare the long trivial rows of the controllable canonic form of the closed loop with the desired ones. Yeah, you try to match those two matrices. Okay, and then you get the answer, K bar. Finally, you have this one. Okay, so it is more tedious to get the solution. Or normally, the performance of this full rank method will be much better than the unique rank method. But again, I want to pose the question. If you look at the whole calculation procedure, are we going to get only one solution in this way? Or there could be multiple solutions again. Are we going to get one solution or not? Yes or no? Some students said no. So therefore, in which step, which means that in some of the steps we may have multiple ways. Which step we may have multiple ways? Which step? Some students said C. There is only one way to specify C. There is only one way to construct the T. AD, okay, very good. Many ways to design the AD. Okay, I'm going to show you the example. For the previous one, what are the other ways? This is one way, right? I showed you, okay, this is the way I used, right? I would say I decompose into S plus 1, and then there is a quadratic factor. So in some ways, right, I consider it as two subsystems, right? One in the first order, the other one in the second order. But I can just multiply all of them together, right? And then I can get a matrix. This is a matrix, you know, for the single input case, right, where you use this whole polynomial, you take out those coefficients, right, put as the last row. Although we say the single input case, we treat this one should be the trivial row, but doesn't matter, right? I have two trivial rows, but anyway, only use the second one. Second, as long as the second trivial row match the canonic form. This one, I'm just consider them as the non-trivial row. Then I'm going to design a K to match those two rows. And you know, since those two rows are different, right? You'll definitely end up with different answer. Okay, is that clear? And also another way say, okay, hey, how, you know, I can also rearrange, right? I can put s plus 2, and then I can s plus 1 times s plus 3 together. Then I get a different way, another way to specify those two sub matrices, right? Okay, so therefore you can say there are different ways. You still get a different answer. Okay. The key point is that the trivial rows, right? Okay, let's summarize. Right, they say the controllable canonical form can be used to solve the power placement problem for both single input and multiple input system. Given the set of desired poles, right, which means we are given the correct polynomial by D, there are multiple ways to construct the controllable canonical form matrix with the same poles for the multiple input case, because there are multiple non-trivial rows in the matrix to specify. You see? Right? There are multiple non-trivial rows. There are two non-trivial rows, so therefore we have different ways to specify the two non-trivial rows, right? The control gains are designed to match the desired controllable canonical form matrix, because there are multiple ways to give you the desired matrix. Therefore, the solution will be different for different design, right? There are multiple solutions. Okay, now think about the case. If there is only one input, and if you are given the desired correct polynomial, how many ways can you construct the controllable canonical form with a given correct polynomial? If there is only one input, how many ways? There is only one way, right? There is only one way to construct the controllable canonical form, because there is only one non-trivial row, and that non-trivial row, the values are completely determined by the correct polynomial. Those numbers, the non-trivial rows, right, are completely given by the correct polynomial. There is no second way, right? You only have one choice. Okay, is that clear? Okay, let's summarize what we have discussed today. So for power placement, right, we'll give you the reasons. Right, we want to meet the performance requirements. We design a reference model. We know the desired position pose, right? We want to change the pose of the system, right, to the desired ones. Then we give you the condition such that we may have a solution. The system has to be controllable. And then because it is controllable, we can get the controllable canonical form. From the controllable canonical form, where we derive the solution. Okay. Then how are we going to do that for the single input case? Which I show you two ways. One is direct comparison, right? The other one is just use the Eichmann's formula. Okay. Now, we also discussed the solution when there are multiple inputs. Then, actually, I show you 3 ways. I show you the 3 ways. The first one is direct comparison. I show you that, and you know there are infinite number of solutions, right? You have more unknowns than the number of equations. Okay, and then we say you don't like the too many solutions, we can use the unit rank method. In this way, you convert the multiple input to a single input because you know a very simple solution for the single input case. And then there is a full rank method, right? This way, you try to exploit the power of all the inputs. Okay. Then we use the controllable canonical form. But we know there is a big difference between the controllable canonical form and of the single input and the multiple inputs, right? The number of the non-trivial rows, right, are the number of the inputs. Finally, I want to give you the answer to the following 2 questions. For single input case, how many solutions can we get for the power placement problem? It's only 1. You can apply the Eichmann's formula, right? There is no other solution. For multi-input case, is the solution unique? You may get multiple solutions. It doesn't matter which method you follow. Okay? So let's say if you encounter questions, right, in your exam, if I didn't ask right explicitly which method you want to use, of course you use the quickest one, the simplest one, probably right the unique rank one, right? But if I ask you, I specify, hey, you need use the 4 rank method, right? Then you have to use the one I specify. If you don't use that one, of course you are going to lose the marks. Okay. All right. I think if you are not clear about the computational procedure, there are more examples in my tutorials, right? Okay, you understand. But first of all, what I said the most effective way is you have to work out the answers by yourself first. Then you will know which part you are not clear, right? And then you look at the solutions. Don't look at the solution directly. If you do that, you don't know what is the difficult part. You don't know. Okay, so that's all for today. I will see you next week. Thank you.